Oh, well. Well, so just so this is discussion session number 3, and today we had 9 talks. They may be somehow described as very subjects is very wide. So, but they cover QCD, hadrons, and hadronic or quark-gluon matter. They may be separated to somehow a bit different subjects. So in the morning we have 2 talks, general talks on confinement, covering the mechanism of confinement and string mechanism. We have 3 theoretical talks, and one, I would say, purely I would say general theoretical talks by Alexander Kamenihidze on the just general approach to 4 particle wave functions, and 2 talks somehow combining theory and experiment by Oleg Zenin and Tamas Chorgo. And Tamas asked, told that he will be busy in the first part of our discussion, but he will be available after 6 o'clock. I put some links, in a sense, a bit maybe approximate ones. So here the relation between first 2 are just obvious. The talk, just tetra-quark theoretical talks, also of course related to LHCb. There is a relation and there are 4 experimental talks. They're somehow a bit related. The relation between Alice and LHCb talk is not only because they are both from LHC, but also because the heavy quarks plays important role also for heavy ion collisions. And of course, the OKA talk and NI664 talk are related because just relation of dark matter and in particular axions. Well, so and we can start with the questions, general questions. Some questions during the talks, but just we can start maybe by general questions to the talks, maybe starting from the beginning. Точно пока не знаю. Возможно, с утра, да. Well, so just actually concerning the talk of Zahar, I remember the question of our chairman related to the relevance of the gluonic correlate also to hadronic physics, right? And also I put here the link to the talk on Oderon, because it's known that Pomeron can be related to just non-perturbative propagators, and maybe Oderon also. But here I don't see. Is Zahar with us?
No, I'm not sure he's there.
He is not with us. Actually, I was going to ask whether just applying these correlators to hadronic process, isn't it possible to relate the scale of Hyatt-Wist to the string tension? Maybe, because both are related. Anyway, if Zahar is not with us, but Vitaly is certainly with us. So what about questions to Vitaly? General questions. Is everything is clear to everybody? Well, maybe.
May I, Alec, do you
Yes,
listen
yes,
to me?
yes, please.
Okay. Yeah, actually, because Zahar is absent, I think that Vitaly now is the only responsible for everything concerning the non-perturbative QCD and so on.
Sure.
It's not a question what I want to say. The first, when people discuss problems related to deconfinement, confinement, and so on, and they use something which is not observable. I mean, correlation functions, monopoles, strings, Polakov loop, etc., etc. In terms of this, it's very easy to argue about confinement or deconfinement. But when I come to reality, the only thing we have in mind, in hand, these are only cross sections, which we can measure at the accelerator, or maybe plus some kind of decays and so on. And that's my hesitation in this field is that I would like to ask, maybe not just for this moment, to try maybe to translate the discussion of these important problems related to confinement and deconfinement in terms of observable quantities. That's my goodwill, I would say. Okay, thank you.
So I understand that this question addressed to me, and it's of course the difficult question. We are still working in a more simplified, say, theory, fluid dynamics. So we are trying to understand the structure and properties of the flux tube between static sources. How is it relevant to phenomenology? It might be relevant for particles with at least two heavy quarks. This is what I can say. Which observables, which quantities can be measured in experiment? This is a too hard question for me at the moment. I cannot tell you what what can be measured on the lattice and then predicted and measured in experiment. In this respect.
Vitaly, I don't expect from you immediate answer to my question. I understand completely that it's a very difficult task. This is just a goodwill and maybe the demand to you to think about that. Is it possible to relate all these beautiful things you discuss to measured quantities? That's not even a phenomenology, just direct or indirect relation of what you discuss with experimental measurements. Certainly, this is very difficult. I don't wait from you immediate answer. Yeah. Just thank you very much. I would like just to pose the problem. That's all. Thank you.
I understand. Yeah. Okay.
If I can, I have maybe slightly related, very naive question concerning Cornell potential. Well, if to relate Cornell potential with flux, well, a linear path is related to tube, so flux is confined to tube, right? And the Coulomb is related to flux, which is distributed along just in the independent on the direction, right? Like in Coulomb law.
No. Coulomb is at large distances, a Coulomb path with a fixed coefficient predicted by effective string theory is related to fluctuations or quantum modes of the string. It is not usual Coulomb. Usual Coulomb we have at small distances.
I see. I mean usual Coulomb at small distances. So if I have naive picture of the flux, which is just distributed in all direction at short distances, right. and then from the tube at large distances. Maybe instead, this is of course maybe this is not so important, but if looking from the point of view of flux, maybe instead of adding Coulomb and linear, one may somehow have a matching of Coulomb at short distances, at linear at large distances. And this would correspond to the flux, which is changing from just isotropic at short distances to tube at large distances. Or maybe this is too naive. This recalls, I am saying because, for example, it's possible to match twist expansion in inverse power of Q square and say chiral expansion in the just direct in positive powers of Q square. Isn't it possible to match linear and Coulomb and inverse?
What do you mean by match?
I mean,
you have running coupling.
Sure. At short distances, I have running divided by R, and at some distances, matching distances, I match it to the linear, and this corresponds to
but you see,
is isotropic at short distances and tube at large. But you said that isotropic is also manifested at large, and it corresponds to fluctuation of
the string. Yeah.
Okay. So this means that this procedure is not taking into account the fluctuation of string. Okay.
Right.
Okay. With your assistance, I found an answer to my question. Okay. But we so should other also general questions to Vitaly, who is responsible.
Excuse me, Oleg. May I ask the question to Vitaly?
Sure.
Thank you very much. I have maybe a rather simple technical question, which probably you know the answer. When you are speaking about monopoles, which are so important in your analysis to understand, to try to understand the possible effects of the confinement. How are these monopoles, which are considered in your considerations in SU2 and SU3 Young-Wills, are they related, and how are they related to these very deep discussions of the monopoles, which you heard probably yesterday, but I have seen only today on the transparencies and presented in the talk of the Professor Mikhail Volkov?
Excuse me, who presented the talk?
I guess this is the talk yesterday. The talk of Mikhailas Volkov, Black Holes with Electroweak Hairs, and he had very deep discussions of the story of monopoles and understanding how they are appearing. And so 12 monopoles, and of course monopoles in electroweak theory. What are your monopoles? What is the place of your monopole? Maybe the place of your monopoles in these studies and considerations. If it is possible, maybe it is possible to open his presentation and to have a look on this discussion, because I think that these subjects may be related to the discussions of the previous day.
Oh, I don't think that they are related. Most probably the discussion was about monopoles in a kind of Higgs theory, right? Here we are discussing QCD, and
of course,
at the first sight, there are no monopoles as classical solution, at least with finite energy in QCD. So to introduce kind of
but in general, there's the solutions of definite equations.
In our case, QCD, we do not consider.
What is the difference?
Solutions of classical equations of.
What is the difference? Okay.
Mm-hmm. So they are different.
And what is the difference? What is the difference? Where are these differences sitting?
there is no scalar field in our case.
No scale. So are they different monopoles?
You see, we are finding monopole-like fluctuations of the gauge field.
Okay.
So locally, they look like monopoles.
They look like monopoles.
Right.
So they are not these monopoles as considered in electroweak theory. They are not monopoles as they're considered by Dirac monopoles. They look like monopoles.
No, you see, they look like Dirac monopoles, I would say.
Okay, they look like,
but they are color magnetic monopoles. They're not electromagnetic monopoles, of course.
Okay, so they look like Dirac monopoles.
Right.
And these are just the generalization to the case of the QCD. Okay, thank you.
Okay, thanks. So we should move, I guess. So other questions to Alexander Kvinihidze? Very.
Yes, I have
Please,
a question.
Please.
Sasha is here. Sasha is here.
I'm here. Do you hear me?
Okay, Sasha, my question is, I don't say simple or not, but in your presentation, first of all, I would like to make you a compliment that I believe that your approach to multi-quark states is seems to me the most promising because it's based on definitely established equations and so on, and relation with quantum field theory is the most direct, and that's very good. But what I want to ask about is you use very often in your presentation the 1, 2, 3 particle irreducibility, but the very notion of the irreducibility is related with cutting of Feynman diagrams or else anyway. But if we take into account the confinement, if the cut is non-zero, it means that you take propagators on shell, and if for example, if you consider quarks, if the quark propagator has imaginary part, delta function, p squared minus m quark squared, it means that in this case, according to Haag theorem, you know certainly about it, we can construct asymptotic state. And this will be in kind of contradiction with confinement. So did you think about this kind of things in your formalism or not?
All right. The thing is that for me, look, let me start a little bit earlier stage. My work last 10 years on the tetraquark was just reaction on usage of my 30 years old equations by actually many groups which call their approach this continuum QCD. I guess do you know this term?
What?
By some reason they call this continuum QCD, meaning that they are using the integral equations. Although they at some stage.
No, I didn't follow actually this trend, and I was just
right. Sorry. No, I did not come to your question yet. So as these people were using the equation, so my first reaction was just to fix some inconsistencies in the equations they used for important physics. Right? And these inconsistencies have been on the level of foundation. That's why my talk was like it was emphasized by Oleg, formal one. So, and being this formal one, for my equations, you need only to know that wherever you have quark lines, it's just input as a quark propagator, no matter how do you derive it. You can derive it as a confined one, which does not have a pole on some mass, right? Or if somebody wants, it's his right to use it like some quark with some mass. So for me, it was not I did not address this question because it would be relevant to at this stage.
Mm-hmm. No, it's
And
very
I'm sorry,
question.
just once I am asked the question, I want to explain my statement about my equations, actually our equations, to be exact. When I say my equations are exact, I can say it another way. In another way, that my equations allow systematic improvement of the description because everything is defined precisely, which was missed in the previous considerations.
Okay, thank you very much, because I completely agree with you, and that's why I believe your approach is most promising, because other approaches, phenomenological with potentials or even with strings, are not elaborated to the degree they could be used formally with all mathematics, renormalization, green function, and so on. So don't stop and go on. Okay, thank you.
Yeah, thank you very much. And just as an excuse of being so formal, I should tell you that there is a, how to say, it could be that in the nearest future, people who are using these equations to describe some physics, they will involve me in the studies, in the phenomenological studies. Of course, from this formal side, but this way I will learn more than I know now.
Okay, thank you. We are waiting with impassion. Okay, thank you.
Actually, if I can, I would add to this discussion that the cuts appearing for, of course, in colosinglet states, the cuts corresponding to cutting the quarks and gluons if necessary, by quark-gluon duality should be substituted by cuts corresponding to hadrons. This is exactly quark-hadron duality, and because there is a full set of states. One full set is quark and gluons and other hadrons. So I believe that here already being formal, by supplementing these ideas of quark-gluon duality, quark-hadron duality, the Alexander work is already applicable. Here I would add that sometimes these cuts based on confinement arguments, they sometimes in some models are removed. I think this, in the spirit of quark-hadron duality, they should be kept, and they should be in the sense that they model the cuts corresponding to hadronic cuts. This is what I just wanted to.
Thank you.
This is interesting. This is interesting. I believe a very important question. Also, this is one phase of confinement. I believe that you have full set of fundamental states, quark and gluon, and the full states of hadronic state. And these full sets just are complementary. This is exactly the complementarity. And at some point, Feynman wrote that the picture of quark-hadron duality, he was speaking about Bloom-Gilman duality. This is what Bohr would like very much, because this is exactly complementarity. Okay. So
thank you, Alec. May I say a couple of words?
Sure, please.
First of all,
Alec, to your comment, I can only smile skeptically. That's all. Let's stop. Yeah, okay.
Yeah, okay.
All right, Oleg. So what I wanted to say, just thank you for at once you have reminded me of this Volodya's question. Volodya's question about cutting cutting the lines. When I say cutting the line, it does not mean to take imaginary part of the, for example, quark propagator. It's just diagrammatically. That's the way the irreducibility and reducibility is defined in context of my equations. This is first one. And second, I actually, when I went to the picture of quark, diquark, anti-diquark, or two mesons, in this in this way, I actually, my cutting were just, all right, well, let me tell another way. It was just, it corresponded to the approximation of two quarks by diquark, right? Or quark, anti-quark by meson, so that the diquark or meson pole features in the equation. This form of equations also I have written in my files.
Well, fine, fine, thanks. So just really, you see, quite interesting discussion relating mathematical, formal, and physical problems. Okay, so we are moving, and we are.
Sorry, Sasha, excuse me. Probably I missed. You mentioned this at the beginning of your talk. That when you were speaking and saying that you have some, you pronounce the word, okay, Feynman diagrams, but my Feynman diagrams are different from the original Feynman diagrams technique. Nevertheless, I will call this Feynman diagram approach. What do you mean by this? Well, telling us these words. Of course, you have some diagrammatic approach. You have some special diagrammatic approach, but they are not derived from the Lagrangian and so on. So what is the difference? May you just explain in few words? What do you mean?
If I understand, if I got you right, I can tell you, I think I was just using this usual diagrams. Maybe what's called, how they are called, when, for example, where the quark propagators are completely dressed. Mm-hmm. It has some special name. Or vertices are completely dressed. There is no bare things there. That's what you mean.
There is no bare things. There are no you do not renormalize.
They are already in the dressed things.
Everything in the dressed things, and that is why probably these diagrams you have shown us approximately may be rewritten on the language of the Feynman diagrams in the concrete, say, QCD model or something like this. Is it possible?
Say it again, please.
Is it possible that your diagrams you have shown for your equations may be rewritten on the language of the Feynman diagrams which were obtained, which can be obtained from the Lagrangian original Feynman diagrams?
Yeah, right. But you know, like you can take some sub-diagram from my equation, like the simplest one would be quark propagator, and then do whatever you want. You can investigate this quark propagator just on the basis, just starting from the bare vertex and then dressing it as much as you can. You can't do it. Exactly.
Okay.
Thank you.
Yeah.
Okay, but now we move to the next talk by Alexenin on the G-2 for muon. Just it was already discussed during there were questions during the talks. Actually, let me start by quite naive question, because as it was understood also after the question of Andrei during the talk, that the recent data are taken into account in this analysis, right? And it's known that the recent data differ substantially from the previous data, recent Novosibirsk data. And somehow what appeared is, and it was not somehow during the talks, the authors from Novosibirsk somehow were very cautious in explaining why there is such a difference. And somehow I saw already some plots that with new data the relation with standard model is quite just is much better. But from in this talk, it shows that the new data are taken into account, but the difference with standard model is still significant. So how to explain all this? Why just in the how can it be explained the difference between the result of this talk and the statement which appeared that the relation to standard model became much better?
Yes, in the original CMD3 paper where this better relation was reported, they did a very simple thing. They excluded every experiment in the range covered by CMD3. It starts from 300 MeV, just above 2 pion threshold, and up to 1 GeV approximately. They excluded every piece of other data, including CMD, including very precise frascated data measured with the radiative return, and so on. What we are doing, we retain all other experiments, which in terms of the number of data points, they far exceed what CMD3 contributes.
Sure. I see.
They have a comparably fine-grained binning in center of mass energy. So for roughly speaking, for every CMD3 point, we have 3 points measured with sub% accuracy by Chloe frascating experiment, by Bebar experiment, and as well as points from CMD2 and another Novosibirsk detector, CMD, and so on. So CMD3 enters this global fit with a weight of roughly of 1/5, given the number of other experiments included into the fit. If we, in the appendix of my talk, there is a slide showing the result of fit dominated by CMD3 only. For this purpose, we exclude all modern measurements in the same energy range, which are comparable with experimental precision to CMD3, and leave only less precise measurements made, say, before 1990s. And we get a similar result similar to what CMD3 demonstrated in the original paper released in September.
I see. So if CMD is substitutes all the previous data, then it's good for standard.
Yes, but
if it combined as you do, but if it is combined with previous data,
yes, if we combine this with earlier measurements with a comparable precision, it just spoils the quality of the fit. It decreases the probability of the fit.
And the reason for difference between CMD and previous data remains also a bit mysterious, right?
Not so mysterious. Again, in the appendix there is an additional slide which actually quotes a recent talk by a CMD3 author, as far as I remember, Logoshenko.
So Logoshenko, the spokesman of CMD3 laboratory.
Yes, and he participated in CMD2 experiment before they migrate, and so he devoted about maybe 20 slides to comparing systematics, potential emission systematics in CMD2 and CMD3, and as for the time being, they came to no conclusion.
I see. I see. So this means I would call this mysterious.
Yes, yes. CMD3 will devote several dedicated runs next year just to refine the systematics.
I see. I see.
Just make the measurement more similar to what CMD2 did in terms of detector subsystems and so on. So if they confirm the result published in September, at least it's on archive. Journal publication is delayed for obvious reasons. Then there will be a question to other measurements with different technique. You see, CMD3 uses a traditional energy scan. They just change the beam energy and scan over raw peak from its left slope to the right one. Frascati measurement made by Chloe experiment is performed with a fixed beam energy. They are sitting in phi meson region and use ISR events to derive the 2 pi form factor at lower energies. So the technique, the detector is completely different. The technique is, the measurement strategy is completely different. And there will be big questions to other experiments if CMD3 confirms the result.
I see. I see.
This means that other experiments will have to find some sources of bias in their measurements.
I see. I see. So this work is ahead. Very, very nice.
Mad few words.
We will know more next on the.
Excuse me, mad few words which about in favor of these statements, information which I gained from the discussion with the representative and speaker of the CMD3 collaboration during our discussion at at Baldwin conference. In fact, unfortunately, the difference between CMD3 and CMD2 is not so mysterious because they do not understand it. In fact, why is the difference? There is the new detector, absolutely new detector, absolutely new technique, and they are indeed unable to understand themselves. And the CMD2 is the old detector. And even some information on the systematics is at present is partly missed in the tips. So in some sense, they are also asking them, okay, why is the difference is appearing? And what is proposed by Ivan Lukashenko in this long talk on the G-2 conference. So he's telling, indeed, we will try to study very carefully systematic uncertainties of CMD3 collaboration, as you confirmed, also measuring the things which was also measured by CMD2, but he's also proposing to those people who have some information on on this form factor in their analysis to consider very seriously the problem of estimating and understanding systematic uncertainties and possible uncertainties of their previous data using the tapes and trying to think about very carefully an analysis as also. This was the statement and proposal of Ivan Lukashenko.
Okay, thanks, Andrei. So just you confirming strongly what Oleg said.
Absolutely.
Are there some other questions to Oleg? This is of course most important, but maybe some other.
Actually, I would like to continue my question about muon experiment. So I understand that, of course, this experiment is very difficult because the cross-section is very small and there are backgrounds and so on. But I would reformulate the question like this. Is it more straightforward if this experiment obtains the result with comparable accuracy? Is it more straightforward to use this result for G-2 from mu E than from these measurements of colliders that look complicated?
First of all, the region of T variable, T variable, the momentum transfer in T-channel scattering is limited. Is limited by the center of mass energy and from above. So it will, I guess, it will be limited from below by angular resolution of the experiment. So as far as I understand, this is mu on E. Authors declare that vacuum polarization in space-like region can be extracted with similar accuracy as from the time-like data. There will be some additional assumptions which would allow to complete some extra data should be added to evaluate the parts which are not, which cannot be directly fitted by fitting vacuum polarization from the d sigma over dt. In South, they expect to get a similar accuracy. The T-channel scattering experiment will be more straightforward in the sense that while using time-like data, there is always a possibility that some all neutral states are missing. Suppose we have some small contribution from, I would say, photons, the S-channel photon is converted to a sigma meson, very wide resonance, and there is another photon in the final state. Then if sigma decays to 2 photons, this is E plus or minus to 3 photons. Process with a huge QED background, so calculated very precisely, but such things can be easily missed in the time-like data. In that sense, mu on E results will be more straightforward.
Okay, thanks.
And I would like just to add that when using time-like data, we use the well-known representation for hadronic contribution to the G-2. Derived by Peterman more than 60 years ago. And there is a similar representation for T-channel input. So one can be, so methodically, it will be comparably complicated calculation.
Okay, thanks.
Okay, thanks to Oleg, and I think we should move. And
before you proceed, let me know that Zakhar Haidukov joined the discussion session.
Well, she just that's what, but well, if still, I think that we now continue to. I hope if Zakhar just joined us, he will stay with us. But now also Tamas also joined us, and his talk is related to previous one because it's also just extraction of new important physical results from recent data. So just now order on. So I would suggest to go to discussion of talk of Tamas. Just
thank you. I also prepared some slides if you want. So. But there are some questions.
Oh, please. I think it's so I guess I can stop sharing.
So I can share screen.
I see. So just I think I should stop Share. Okay.
Okay.
Please do that.
Thank you.
Yeah.
And then I go to first the presentation mode, I think. Just a sec. And then I should try to share the screen. Share. And this one, maybe it's not perfect. Do you see it?
Just maybe you can make it also full screen, but it's
Is it visible now?
Fine. Yeah.
Okay, so I wanted to show some cross-section results, which I didn't have time to detail. And so these are published, but I would like to know that these are kind of extrapolated out of the domain where we know that this Glauber type of BLS-Zach model is valid. So the model is not fully calibrated in the low T range, but it nevertheless gives a very good description of the total cross sections. And you see that calculations for proton-proton and proton-antiproton indicate very similar total cross sections, but we have also the Pomeron contribution, which is really the same as the proton-proton and the proton-antiproton. And I think it is not yet a fully calibrated result, but it's indicative. And then you can take the logarithm of the total cross section and plot it versus logarithm of energy, and then you can read what is the Pomeron exponent, and the value is about 0.07, 0.075, and this is a normal Pomeron intercept, so to say. But we should stress that we use the Glauber's multiple diffraction theory and not Regge phenomenology, just the result is converted to an intercept. But then we can do the same for the Odaron because we have the Odaron amplitude. And the first important thing is that at 1 TeV, the contribution, so we take the imaginary part of the Odaron amplitude at t equals 0 and evaluate this total cross-section contribution from it. And you see that actually this is very small, even within the maximum error bar ranges about 0.1 millibar below the measurable quantity. And if you take the logarithm and plot it versus the logarithm of energy, you can see that the slope slightly decreases, but still the Odaron intercept would be 0.33 at 7 TeV, 0.32 or 31.5 at 8 TeV, and this is anomalous. So this is larger than the PQCD expectations, and it decreases very slowly with S. So this means that we seem to find a threshold effect, and not yet in the domain where we have. And then I have some poetry if you want to discuss, but let's discuss the science. That's it. Thank you. Oleg, we cannot hear you. Your mic is off.
Okay, thanks. Quite interesting, but also if the intercept of Odaron be larger than that of Pomeron, wouldn't it violate positivity at some point?
No, I think it is clear that these extrapolations are very preliminary and they cannot be used above 10 TeV. So it is just a threshold effect. That's what I mentioned.
May I ask you a question? Here is Mikhail.
Please, Volodya, please.
Can you see, I'm sorry that my camera doesn't work, but you can see my picture here. Can you see my picture there?
No, I stopped. I will stop screen sharing, and then maybe you can do that. Just a second.
I would like. Okay.
Just a second.
Can you see my screen here?
Wait a second. I still now I stop.
Yes, my question is, they have already trajectories and the Pomeron in the whole region.
Sorry, I still cannot see your picture.
Okay.
You should share.
Okay, let me.
Please share your screen.
Okay. Check out. What about this now? Can you see my screen? No.
No, I see Oleg.
Because my camera doesn't work at this time.
Probably
Maybe I'll do
futures.
it later. But I can just ask you without these pictures. My question is about data obtained from Jefferson Lab, class collaboration. This vector production of vector mesons in hard region at high transfers, large transfers. And this region, description with using of linear region trajectories are not appropriate. We have to describe the data, we have to use saturating region trajectories, which have
As I mentioned, it seems that we see a threshold effect and we are not in any linear domain. And our extrapolation doesn't work above 10 TeV. So we are working on extending the range in T and in S. But I cannot tell about asymptotia. What we are saying is that we do not have a simple Regge phenomenological result, but we have a simple Glauber's multiple diffractive theory result that seems to be extendable down to low T, and we try to extend it to larger S above 10 TeV.
Understood. Okay. I see what you want to say, but let me ask you, do you think that region trajectories and the Pomeranian also are linear in the whole region? Because you know what, there are data that show that not linear trajectories are not true in the scattering region. They are not linear there in that region. Because I just cite publications.
I agree with you. We don't claim any linearity in the Regge trajectories.
Regge trajectories at scattering region are saturated and have asymptotic behavior equals to -1 at transfer momentum going to -infinity. Because at this point we have that Regge trajectories and Pomeranian trajectory also, they have two asymptotics. At high positive transfer momenta, they are almost linear, but in the scattering region, they have asymptotic behavior equals to -1. This is universal asymptotic for all leading region trajectories. And I just cited this time works published by Vladimir Petrov. I met him in Gonel, Zolotoye Peski, and we have spoken about behavior region trajectories, especially, I mean, Pomeranian trajectory in the scattering region. And there are data also. I would show you because
I'm sorry, but I would like to follow this up by email exchange. I don't have to say anything, but I would like to listen to the question of Professor Petrov himself.
Yes, no, Petrov knows maybe my words because I would like to thank him. I will thank him for kind invitation to this workshop, and I would be glad to come to this conference, but I am here in Belarus, and not so easy just to go there at this time. That's why I just communicate with you online. But it would be good to meet us together and to discuss this in more details. And I also
agree.
wanted to discuss this question with Vladimir Petrov because he knows this subject and he is devoted to that, and we would discuss and maybe would find some positive decisions for many questions. Because I do work not only in high energy physics, I just work in other topics in other fields, quantum mechanics, and my report is going to be, it will be on December 1st, devoted to solution of Schrödinger equation. But it will be on December 1st. Thank you for your attention, and hope to talk to you on December 1st. But the question is very important. Look at this data. Maybe you can find this everything. All the data can be found published by class collaboration. They cite my publications devoted to Regge trajectory, especially Pomeranian. Pomeranian is very important because it gives important and not important, just the biggest contribution to the total cross-section. That's why Pomeron is a very important object. Also, there is my article published in EPL in 2010. And we can look at this paper. You can find my publications devoted to Pomeron and trajectories on internet. It's
okay, thanks. Volodya Petrov, would you like to add something?
Yes. You see that half an hour from the drink, I would like to avoid any kind of complicated questions concerning the reds, the trajectories, and so on. So my question to Thomas is simple, maybe not very simple. What do you think now? How can you comment this tension between the totem and atlas measurement of the total cross sections?
Thank you for this
because
question.
There is a 3 sigma if they
I know this, so I would like to comment. I think it's a management problem. I know the issue. I confirm that there is a tension between atlas and totem total cross sections, which at any single energy is just a kind of indicative difference. But if you combine all the data, it seems to be a different trend when we try to fit it with the same excitation function. The confidence level goes to 0 or less than acceptable. So I think it's a CERN management problem. They should have kind from the directory.
May I ask you one thing?
But let me just finish the answer first.
Yeah,
so the main point is that they should sort out the difference. It seems to be a normalization problem. Please go ahead.
Okay. Could you please send me how you combine two data in order to obtain something? Not, but let's send me just your consideration. How should we combine atlas and totem measurement of the sigma total in order to have some
this is a good question, and I would like to answer immediately because the answer is simple. What we do is we fit separately the atlas data, we do separately the totem data and check if the parameters are within error bars the same, and we also try the combined fit, and we find that the confidence level of the combined fit is too low, so you simply cannot combine the total cross-section measurements, unfortunately. And that's a problem which should be sorted out by CERN management, but I don't think it's feasible. They should have done it already. So we probably have to live with the tension between the two data sets and analyze them separately. Thank you very much for this question.
Thank you, Köszönöm. Thank you.
Okay, thanks. And I am afraid that now we just, it's now 18:25 Moscow time. So I'm afraid the time for our discussion is already over. There are still 4 very nice experimental talks. But I'm afraid that just we don't have time. So probably just or we have some extra time, Vitaly.
Okay, this depends on audience, not at me.
Because there is something in the it should be some conference dinner,
if
right?
people are interested in discussion, then why don't we continue?
Well, we may continue just to have first to finish with theoretical things. Are there some more questions to Zakhar Haidukov? If there are. So we continue, and if it would be necessary, to go to eat, well, just people who are offline can do that, and online people can eat independently, right? So just questions to Zakhar. Are there any more? So we already discussed that somehow interpreting Zakhar's talk. And just if not, when we can move to experimental talks. First, just probably to Alice talk. Are there just questions? By Evgeny.
Excuse me, may I ask the question just to Alice talk? Maybe this is not related to this subgroup, but whether this is true. During the Lomonosov conference, I heard the talk of two representatives of the Kurchatov Institute who were considering very seriously on the Alice collaboration to try to extract the value of the tau lepton anomalous magnetic moment sign in future. Whether you heard about this project, and if yes, what is are they really going on? Because we know that for the tau lepton anomalous magnetic moment, the previous experimental data of Lab and other groups, they are not indicating, they are not giving even the information whether the experimental result is positive or negative. They are not catching the sign. Do you know anything about these studies, Evgeny?
Yeah, in fact, Evgeny has already left. He's catching his Sapsan train to St. Petersburg.
Okay.
This is
okay.
Yuri.
But then maybe
collaboration.
Okay. After
so I can answer your question. So, for the magnetic field effect, we are measuring the polarization of baryons produced in heavy ion collisions in semi-central collisions when we have some non-zero impact parameter. So in this kind of collisions, we expect that there will be strong electric current or chromamagnetic current of the nuclei, and in this case, the particles which are produced from this non-central collision should be polarized. So we have this measurement, and probably this is not enough accuracy of this measurement, but there is already clear indication that the baryons are polarized, and it could be one of the possible explanation. This is just
so in principle, in future, this can be done just in time.
Well, we have just analyzed data of run 2.
Not now.
Very little statistics. 1 month ago, we have collected 40 times more data from lab collisions. And now this data analysis has just started. So maybe in a year or 1 year, we will get much more precise measurement.
Okay, thanks.
So just stay tuned and we will see.
Okay, very nice. I think because of limited time, we should be concentrated mostly on the talks. So second, now, so we move just to the talk of Dmitry, right, on LHCb. Are there questions to Dmitry on heavy hadron spectroscopy? It was, well, I think there are, I would say there are a lot of interesting questions, but probably it's maybe difficult to solve them during this just short discussions. Only 1 hour for 9 talks. So if there are no questions,
may I have question to LHCb. So in fact, I see that LHCb is trying to find some multi-quark states like tetraquark, pentaquarks. In Alice, we do the similar measurement, but we don't try to find these states. We just measure the correlation functions between baryon and meson, or baryon, and these correlation functions indicate that there is a strong interaction between baryons in the QCD matter. It could be also the same nature as we observe in the multi-quark states. So do you have any any thoughts about these interactions which are not measured directly in the invariant mass spectrum, but just in the correlation functions between different hadrons?
No, I should say that the studies of the multi-quark states is in HCB. So in principle, we have some searches, but I can say something about the possible signals or parameters of such states, but only what I can say that such studies are performed in our experiment. But about the publications or results, it will be in the near future.
Okay, thanks.
Thanks. So, well, if there are no more questions to Dmitry, so we move to another experimental talks related just to dark matter and axions. So we start with talks with questions to Vladimir.
I think Vladimir left.
Vladimir left. So
maybe he's online. Let's check. Wait a second. Is he online? No, he's absent.
Well, when the NA64 to talk, Mikhail is with us. Is he here?
Yes, he's here.
Yes, so please questions to NA64. From just audience and Zoom. Yeah.
Okay, Mikhail, may you just ask you the question, just I'm understanding that which may be related to the question of to the studies of obras which were done in OK experiment. To my understanding, you are trying to put bounds on heavier axions, while OK experiments are looking for rather light, putting some bounds on light axions. Is this true?
Yes, we are looking for axion-like particle, and this is not from some decay. So we don't have limitations from this side. But we have other limitations. The point is that heavier axion-like particles are more short-lived. And we cannot search such particles in our methodics.
Yeah. So these are complementary bounds, the bounds in the different kinematical regions.
Yes, independent kinematical regions.
Independent kinematical bounds. Okay, thank you.
Okay, so just if there are no more questions, to just I see there are not so still some people are here, but just we already had some discussion. I would say very nice for such limited time. So if there are no more questions, I believe so. Let us thank all the speakers again and all the participants of discussions. So just we close, right? So for
yes, thank you to discussion leader as well.
Thanks. So just offline participants may proceed right to the dinner, which is identified.
Right. Yeah, you are correct. So everybody is invited.
Okay. Bon appetit.
Thank you.
Bye.
You are not with us.
Bye.